This is the first screencast for Unit 4, so we'll get to 4.1 in a moment. But to introduce Earth systems, excuse me, we need to talk about density. So it's important to know that things that are less dense float on top of things that are more dense. As you can see in this example, if you have a glass of oil and water, the oil is less dense than the water, so it will rise to the top, it will float on top. Another common occurrence for this are things that are hot and cold, where there's a difference in temperature between maybe objects of the same substance or materials of the same substance. So, like hot and cold water, hot and cold air. Right, where hot air is less dense, so it rises above the cold air. So this is going to be a theme that we're going to see throughout this unit, beginning with plate tectonics, where we're going to have hot rock that's less dense floating on top of colder rock that is more dense. But the thing to remember here is the temperature differences cause the differences in density. It's the differences in density that drive this movement of things being less dense floating on top of things that are more dense. So let's get started with Unit 4.1, plate tectonics, and we're going to do a little travel through time here. Plate tectonics did not come into its own as a theory until really the mid-20th century, and it began with this guy, Alfred Wegener, and his theory of continental drift. So what Alfred Wegener said was that the continents seem to fit together like a puzzle, right? Parts of North America seem to fit with North Africa. Parts of South America seem to fit with South Africa, Southern Africa, I should say, not South Africa, the country. And so on. Lots of other countries fit like puzzle pieces with lots of other countries. Not only that, but if you found fossils on coasts of different continents, they matched with fossils on opposite continents. So Signathus or Signathus, a land reptile in South America, fossils of that were also found in Africa. Fossils of the land reptile Lystrosaurus was found in Africa and India and Antarctica. And so these fossils, these animals could have only been in all these places if they were connected, right? Because in this case, they were land creatures. Even plants, same kind of issue. So this was his observations. He proposed that the continents had plowed through the oceans, right? That South Africa had moved through the South Atlantic Ocean. And this was part of the problem, was that other scientists rejected his theory because the continents were less dense than the oceanic rock. There was no physical way for them to plow through oceanic rock. They would have just been destroyed. And so Alfred Wegener's theory was rejected. In class, we'll probably watch a song about it on YouTube. If you want to check it out ahead of time, you can, but then you're going to miss sort of the whole communal experience of the class watching it together. So if you can hang on, we'll show it in class. As the field of geology developed, scientists were able to determine that the Earth actually has several layers. It's not just the ocean and the continents, but inside the Earth, there are four major layers. So in this picture from left to right, you can see the crust, you can see the mantle, you can see the outer core, and then you have the inner core. Now there's some differences between the chemical and structural composition. So the chemical composition is what's on the left. That's what we see talk about most often, where the crust is a different chemical composition versus the mantle, which is different chemically from the outer core and different from the inner core. But the structural composition, like how do these materials behave structurally, is not just based on their chemical, but also based on their temperature. So the crust and the upper part of the mantle, called the asthenosphere, behave differently. 3, 2, 1. But how these layers behave structurally depends not just on their chemistry, but also on their temperature. So the upper layer of the mantle and the crust make up what's called the lithosphere, and so that's the coolest part of the Earth. And then if you go a little deeper, the mantle gets a little warmer, and so while it's still the mantle, the asthenosphere behaves differently than the lithosphere, just based on temperature. And then as you go further down, the outer core is liquid, even though it's similar composition to the inner core. The inner core is solid because even though it's super hot, it's under intense pressure, and that keeps the materials in the inner core in a solid state. So the reason the different layers are layered this way is basically because of their density. So the inner core is the most dense, outer core less dense, and so on up until the crust, which is the least dense of these layers. And this was, again, part of the issue with Alfred Wegener's theory. The density of the continents is less than the density of the ocean, um, the ocean floor. So how could they have moved? It didn't work. Um, a breakthrough was made, in the middle 20th century with Harry Hess, and he developed a theory called seafloor spreading. This was proposed on the fact that hot, less dense magma was pushing upward through the dense ocean floor. So if you look at a map of the world, or I should say the globe, you'll notice that there are mountains running down the middle of a number of the oceans, especially the Atlantic Ocean. It's called the Mid-Ocean Ridge. And these mountains are really small volcanoes where magma is pushing up through the ocean floor. It's hot, therefore it's less dense. He observed that the seafloor then appeared to be forced outward from the opening, hence the seafloor spreading. So the seafloor was getting larger because magma was creating new rock in the middle. And so when you took these two things together, you could see that somehow the ocean crust was moving. So if the continents were sitting on top of the ocean crust, then they could move with the ocean crust rather than trying to move through the ocean crust. So when you take the continental drift idea together with seafloor spreading, what that really leads you to is plate tectonics, where the tectonic plates move around themselves. And as we're going to see, the plates themselves can be both created and destroyed. So we're going to look at specific boundaries between tectonic plates. So we said there's two types of tectonic plates, oceanic and continental plates. So they can have two oceanic plates next to each other. So we could have an oceanic boundary. We could have two continents next to each other. So you have a continental boundary. Or you can have an oceanic plate next to a continental plate. And therefore, you would have an oceanic continental boundary. So these are the three types of boundaries we'll see in terms of the two tectonic plates on either side of the boundary. And then the boundaries can have different interactions. Just because there are oceanic plates next to each other doesn't mean they're behaving the same way. So they could be converging, which means they're coming together, two oceanic plates coming together. They could be diverging, which means plates moving away from each other, or they could be transform boundaries, which means they're sliding past each other. And as we're going to see in the diagram later, the three types of boundaries in general can have all three types of interactions, with maybe one exception. But we're going to see there's going to be overall 8 different types of plate tectonic interactions when you combine the different boundaries with the different interactions. So we're going to look at how all the plate tectonic features fill in with different boundaries and different behaviors, interactions at those boundaries. So for example, if you have two oceanic plates next to each other and they're converging, right, they're coming together, the feature we're going to see there is a subduction zone. And volcanic islands are going to be created, right? So the subduction zone is where one plate goes under the other, and then the subducted plate melts. That magma rises up to the top because it's hot and creates volcanoes and volcanic islands. Japan is a good example of a convergent oceanic plate boundary. If you have two continental plates coming together, we get what's a collision. So they're both equally dense, so they just sort of crumple up on each other, and you end up with mountains. So the good example of this is the Himalayas. If you have an oceanic plate next to a continental plate and they're converging, then the oceanic plate goes under the continental plate, also a subduction zone. But the difference here is that there are mountains created, but they happen to be volcanic mountains. And so you get a feature like the Andes Mountains, where they're continental mountains, but they have volcanoes. We also see this in the Pacific Northwest with the Cascade Mountain Range. If you have two oceanic plates and they're diverging, they're moving away from each other, you get mid-ocean ridges, and you get volcanoes at these mid-ocean ridges. And so a good example of this is the Atlantic Ocean, where the mid-oceanic ridge runs down the middle of the Atlantic Ocean, where it's oceanic plates moving apart and magma coming up in the middle of them. If you have two continental plates moving away from each other, this is called a rift zone, and we see this in East Africa. It's currently the only really active rift zone in the world, but there are volcanoes there, and it's two continents coming apart. Oceanic plate and continental plate boundary that's moving apart doesn't really exist. It certainly doesn't exist on our current Earth. And one of the reasons it doesn't exist is that when two plates are moving apart, oceanic crust is being created. And so an oceanic continental diverging boundary, if it existed, would pretty quickly resolve itself into a double oceanic plate boundary. So we don't see oceanic continental. And then transform plate boundaries, where the plates are moving, sliding past each other, but not one moving under the other or colliding. We see the same feature in all these places, a bunch of earthquakes. So if you have two oceanic plates moving past each other, two continental plates sliding past each other, or oceanic sliding past continental, in all cases we see earthquakes, not really any volcanoes, not really any mountain building. Video that you will watch either at home or in class will be brain pop, so you can get a little nostalgia for middle school brain pop there. One example we see of tectonic activity is earthquakes. So if you look at a map of the world, you can see that earthquakes tend to be clustered in specific places. So along the Pacific Rim, right, the rim of the Pacific Ocean, certain places in the Caribbean, certain places on the eastern edge of South America where the Andes Mountains are, and then where a lot of the mountains are in Europe, we see earthquake activity. This is just one website that shows earthquake activity. Another one is the seismic monitor, which is showing a lot more smaller earthquakes, and so you can see some of these locations a lot better. The east area of the African continent, a lot of Indonesia, up into the Himalayas, and then some places out in the ocean as well. Now, we'll see that volcanoes and earthquakes happen a lot at plate tectonic boundaries, but not everywhere that has a volcano is a plate tectonic boundary. So we're going to talk about hotspots. And specifically, we're going to talk about the island of Hawaii. So there is definitely a volcano there. And yet Hawaii is in the middle of a tectonic plate, right? It's in the middle of the Pacific plate. So if there's no boundary, why is there a volcano there? And the reason is a thing called a hotspot. This is where the mantle magma is super hot. And we don't know why this happens, but it does. And so this hot spot, the magma is so hot, it breaks through the crust even without a tectonic plate boundary, and creates volcanic islands. And so we can see this in how the Hawaiian Islands are arranged, that the Pacific plate has been moving to the northwest for millions of years, and every time it moves, the magma comes up in kind of a different place. And then over time, because there are no new volcanoes on those islands, they get eroded and become smaller and smaller. So the island of Hawaii, also called the Big Island, is where the currently active volcanoes are. And then to the northwest of that is Maui, which is one of the newer islands. And then Molokai is a little bit older, and Oahu is a little bit older than that. And then Kauai is one of the oldest islands in the Hawaiian island chain. If you're curious, the most recent eruptions on Hawaii are at Kilauea, which is on the southeast flank of the island. There are two other volcanoes, Mauna Kea and Mauna Loa. Mauna Loa has been active within our lifetime. Mauna Loa has not, but it's not considered extinct, just dormant. Kilauea has erupted for 35 years, with a brief pause in 2018. Over 800 homes have been destroyed in separate eruption events. And the southeast side of the island is almost entirely new in the last 1,000 years. Back in 2018, there was a big magma drainage event where the Kilauea caldera, which had been filled with lava and other, magmatic rock, magma, for well over 30 years, suddenly drained and dropped the caldera floor down. And so it went from an elevation of around 1,100 feet down to an elevation of 600 feet. So to give you an idea, like it dropped almost the height of the Empire State Building, which is just a crazy amount of drop. Like that's so much magma that just left that caldera. But since 2018, the volcano has started erupting again, and it's a great place to visit. Highly recommend it. All right, that is Unit 4.1, Plate Tectonics. Let me know what questions you